Thanks very much. So I have two purposes here today. Obviously, I'm going to spend most of the time talking to you about the work that we've been doing looking for solar axions over the last close to 2 decades. But I also want to tell you a little bit about my home institution, Lawrence Livermore. So I'm going to bookend my talk on axions with just a little bit of information about the DOE lab complex. I also want to acknowledge the fact that both CAST, the CERN Axion Solar Telescope, and IAXO, the International Axion Observatory, are very large collaborations, scores of scientists and engineers involved with each. But there's 3 colleagues I wanted to acknowledge. Jaime Ruiz and Julia Vogel started off their career at Livermore. I recruited them away from CAST once they finished their PhDs. They're now staff scientists there, and they both have leadership roles in the US for both CAST and IAXO. And then Igor Irastorza, who is the spokesperson for IAXO. He's at the University of Zaragoza, and he's really been the driving force behind what we're going to do after CAST. So a lot of the material here he's produced, and I'm glad to be able to share that with you today. So with that, let me just jump into a little bit about the DOE complex, the National Lab Complex. So there's 17 national labs across the country. Lawrence Livermore is one of those, 3rd largest lab, both in terms of budget and size. And if you think about the labs, they span a broad range of missions from basic science to technology development, and they might be focused on fundamental science questions, or like Livermore, Los Alamos, and Sandia are focused on a number of national security challenges. So some of the labs that you might be familiar with that have multi-purpose science missions include Lawrence Berkeley, Argonne, and Oak Ridge. On the inner ring are labs that are more focused on just a single mission. So Fermilab does particle physics. Idaho National Lab focuses on nuclear power. The National Renewable Energy Lab, you guessed it, focuses on renewable energy. The lab complex taken together represents the largest collection of PhD researchers in the country. Livermore itself, perfect, thank you very much. Livermore itself was founded more than 65 years ago. We're about 40 miles due east of San Francisco. Currently, we're about 7,000 employees. During the height of the Cold War, we were closer to 10,000 employees, so it's a very large campus. Someone has recently referred to this as 1 square mile of happiness. So it's a very, very concentrated collection, both in terms of the buildings, the infrastructure, the facilities, but also it's our founder, E.O. Lawrence, really focused on big science, multidisciplinary science, and so the fact that we're all co-located in this small campus really helps that. We're about a $2 billion a year enterprise, and we're currently operated by a limited liability company. All of the national labs are what are called FFRDCs, federally funded research and development centers. They're operated on behalf of the federal government by the parent organization. That could be a university, or in the case of Livermore, it's University of California and a couple of industry partners. At our lab, there's a few core competencies that we like to focus around and build upon. One of those is high performance computing. This really underwrites a lot of the work that we do. So the DOE is the single entity that pushes US high performance computing. So we work very closely with industry to make the next generation machines. We need this capability for the nuclear deterrence mission, as well as for doing ab initio basic science calculations. This explains why we have, for example, thriving programs in both advanced materials and manufacturing and bioscience. A lot of the work we do takes advantage of the high performance computing. We also do a lot of work in high energy density science, laser optical science and technology too. We also have some pretty unique facilities on campus. Probably the one that's most well known is the National Ignition Facility, or NIF. That's the world's largest laser. It actually is comprised of 192 separate beams. Total power is about 2 megajoules, and you're able to focus all of those beams down to about a 50 micron spot and control the arrival of the pulses at the picosecond level. Before we put something on the NIF, we can do development of an experimental concept at the Jupiter Laser Facility. This is a great place for students and postdocs to learn their disciplines, try out ideas before we transition it to the larger facility like NIF. We also have a couple of centers here that do high precision measurements. They've kind of been round robin with other leading centers across the country. So both at the Forensic Science Center and at CAMS, the Center for Accelerator Mass Spectrometry, we might get samples one day from the FBI. We might get samples from NASA for a return mission where we're doing cosmochemistry. So capabilities like this really support a broad range of missions. So with that overview rather, let me switch to Axions and tell you a little bit about what we've been working on over the last about 15 years. So when I think about the universe, big picture here, right? We have this very exquisite model, the standard model that explains much of what we know. So you have all your leptons, your quarks. This is all the stuff we can touch, that we can see, that emits light. There are some challenges though with the standard model. One of the things we're going to talk about today is the strong CP problem, the lack of charge parity violation in the strong sector. We know that must be violated. We live in a matter-dominated universe. That's an issue with the standard model. There's also things the standard model doesn't talk about. Neutrino mass. It also doesn't give us any handle on dark matter. The two leading candidates for dark matter are weakly interactive massive particles and axions. So axions were first proposed as a solution to the strong CP problem, but they've also been realized more recently as a very likely candidate for dark matter. And the thing we won't talk about today, but is definitely out there, is the rest of the universe, dark energy. So we know from recent supernovae observations, the universe is actually accelerating very rapidly apart, right? And this we just have no clue on. So leading funding agencies, NASA is doing WFIRST, NSF, Department of Energy is building LSST, the Large Synoptic Survey Telescope, to get a handle on this. So again, we know a lot, but there's a lot more that we don't know. So I'm an experimentalist, so please don't ask me to do any field theory derivations. These next couple of charts, I just wanted to try to motivate why we're interested in axions and what problem we're trying to solve with this formulation. So in quantum chromodynamics, you can introduce a charge parity violating term that looks like this. This theta term consists of two separate components. One comes from there's a few different ways to do this formalism. One comes though from the quark mass mixing matrix. The other comes from the QCD vacuum states. So this term, theta, consists of something from two very different origins. We know from the lack of an observation of the electric dipole moment of the neutron, which is very, very small. Theta itself is also very small. So we have this fine-tuning problem. Why is this term so small when you'd expect it to be of order unity, especially when it comes from two completely separate parts of the standard model? So oftentimes when you have this fine-tuning problem, it's indicative of a hidden symmetry. So Roberto Pecci and Helen Quinn proposed this solution to the strong CP problem. So they introduced a new field, which has it's a U1 symmetry that has a spontaneous breaking, and there's a particle manifestation to this. So it was Wilczek and Weinberg that both independently realized that this solution would produce a particle. Frank Wilczek dubbed this the Axion because there's a detergent in Europe, a washing up liquid, and so the Axion cleans up this problem in the standard model, and that name has stuck. And it's got the right ending, pion, kaon, electron, it just sounds right. So a little bit of humor in physics every once in a while. Some basic properties of the Axion: it's neutral, it's a pseudoscalar particle. It has properties very similar to that of the neutral pion, which is very important for the detection techniques we're going to talk about. Most importantly, the QCD axion has this relationship between the mass of the axion and the coupling constant. So this has to do with how easy or hard it is for the axion to interact with things like photons. So the higher the axion mass, the easier it is for that interaction to happen. We'll see that in a second as we go through phase space. All models of the axion have a coupling to the photon, and that really is the primary way that you can search for the axion. There's a scale factor here that depends on things including the ratio of quark masses. So it's not a single line, it's a band. And this scale factor goes by about a factor of 10. The way that you would actually detect the axion then is through the Primakov effect, which was first used to explain the coupling between photons and pions. It's the same dynamic here. So you have an axion, and in the presence of a large electromagnetic field, you can convert the axion to a photon, or vice versa. Take a photon, couple it to a virtual photon from the field, and make an axion. So this really is the key way that we detect, that we look for the axion. So it's an indirect method. It's this conversion of axion to photon. There's also extensions in the standard model, mostly that come out of string theory, where you might have a axion-like particle. It has the same properties, save one that's very important. You've decoupled the mass of the ALP, or axion-like particle, with its coupling constant. I'm certainly not going to get into all of this, but it's a candidate for cold dark matter, for dark photons, might even help explain dark energy. And depending on when you invoke these domain walls collapsing and the dynamics of the axion strings, it might even help explain inflation. Another reason that we're interested in ALPS is it might help us explain some puzzles that we see in traditional astrophysics, and I'm going to highlight two of those right now. One is that we observe ultra-high energy gamma rays from very distant blazars in AGN, active galactic nuclei. So these are the black holes at the center of every galaxy. They're spewing out very highly energetic photons, 100 GeV and above. And those photons should be quenched as they travel across the universe to the Earth by interacting with extragalactic background light. The fact that we see those photons, what might be happening is those very high energy gamma rays actually get converted to axions in the magnetic fields that exist out there between clusters. They would then travel unimpeded, get turned back into photons. These high energy photons, one of the things that's important to note that when you convert an axion to a photon, it retains its momentum and it retains the knowledge of the color of the photon that you started with. So if you started with a GeV photon, turned it into an axion, and turned that same axion back into a photon, you keep that energy information. The other one is anomalous stellar cooling. So we have accurate ages for white dwarfs, neutron stars, and red giants, and in all cases, we see the stars cooling faster than we would expect from basic theory. So that might indicate that there's an extra cooling channel, which could arise from the axion coupling to the photon, or an axion coupling to an electron and letting energy escape from these systems, let them cool faster than we would naively expect. So to try to summarize this, why might you invest a lot of time and energy into looking for the axion? So I always start with, we want to solve the strong CP problem. That in and of itself, I think, motivates spending the energy on looking for axions. It is, by definition, a component of dark matter. It might not be the only component, but if you find a QCD axion, it is definitely dark matter. You might be motivated by looking for extensions of the standard model, and this is where ALPS come in. ALPS are ubiquitous in most string theory or extensions of the standard model. You might be interested in trying to solve these astrophysical riddles. So let me move to the phase space plot next. Okay, here we go. So I mentioned this before, that the game here is searching axion mass, which is on the horizontal scale, versus the coupling constant. So the QCD Axion band I've referred to as this yellow band here. ALPS can exist anywhere in this phase space plot. And then I've shown all the parts of this parameter space that have been excluded either from direct searches or from astrophysical observations or other observational constraints. An example of this is the Planck result, which sets an upper limit on how much hot dark matter there is in the universe. So if you assume that hot dark matter consists of axions, then that sets a limit that's kind of in this region here. This is Helioscopes, so this is the CAST experiment has excluded this large part of parameter space. And then these green bands here have been excluded by an experiment called ADMX, the Axion Dark Matter Experiment. We'll talk about that just in a second. But this is, you're going to see this plot in several forms throughout the day. So again, our goal here is to build an experiment that has sensitivity down into this range here. So let me highlight just very quickly kind of the most interesting part of parameter space. So for QCD axions, we have limits on how massive the axion can be. It's right around 1 electron volt. And there's very strong arguments that it has to be above about 10 micro eV. If it's less than this, it would overclose the universe. There'd be too much dark matter. So if you're interested in just looking for the QCD axion and solving strong CP, you want to look here. If you're interested in these astrophysical hints, the two transparent universe for high energy gamma rays, this would be the area to look for. And if you're looking for anomalous cooling of white dwarfs or red giants, you want to look here. And this could either be an ALP or a QCD axion. And then these extensions of the standard model, it's really, go figure, the theorist will build any model that's not excluded by a search or by an observation. So it's pretty much anywhere that you haven't built an experiment, there lives a model. Okay, so I mentioned this before. When we're looking for axions, we want to use the Primakov effect. There's 3 classes of largely complementary experiments that we can rely on to look for the axions. The first are sometimes called helioscopes. So what we're looking for is cold dark matter axions that were created at the time of the Big Bang that are in the halo of every galaxy, including our Milky Way. So the concept here is that you have a microwave cavity, you put it in an intense magnetic field, and as our solar system spins through, rotates across our galaxy, it's going to interact with clumps of cold dark matter. So if you suddenly see an excess in microwave photons in your cavity, which is otherwise empty, that's a detection of axions. It's a really amazing tour de force in experimental physics. It also has a very large model dependence. It depends on your cosmology. It depends on axions being the only constituent of dark matter. The next class of experiments is sometimes called light shining through walls. This has essentially no model dependence because you're bringing the source of the axions to the game yourself. You take a very intense laser, you shine it through an electric, a very strong magnetic field, and you point it literally at a wall or some kind of block. On the other side, you have a cavity with a photodetector. So suddenly if you see photons, if you started with the green laser here, if you see green photons in your, what should be empty cavity, it's because you've taken photons, converted them to axions, and then over here with your very strong magnetic field, turn the axions back into photons. So very little model dependence. The challenge for this is making a very intense laser and also putting together a big enough magnetic field to carve out interesting parts of parameter space. The final concept are what we call axion helioscopes. And we'll get to the physics of this in a second, but basically inside every star you should be producing axions if they exist. So we're looking for axions that are coming from our sun. The only model dependence here is in stellar astrophysics, and for normal branch stars there's very little physics uncertainty in luminosity functions. So we think that if axions exist, we can really accurately predict their rate and the color of the axion. The other nice thing about this class of experiments is it's gone through several different generations of experiment. CAST is a third generation experiment. We understand how to improve the sensitivity. These other two types of experiments need, I won't call them miracles, but significant technology development. We don't need that for the next generation beyond CAST, the IAXO experiment. So we're ready to go today. It's really funding limited. Okay, so let me walk you through this very quickly. So inside our sun, we have a thermal spectrum. It's just a black body spectrum in the soft X-ray. So 1 to 10 keV photons in very high density in the stellar interior. We have really strong plasma fields, so that's the EM field. So these X-rays can be converted to axions, and they stream out of the sun. 300 seconds later, they're going to hit our laboratory. They're going to hit the surface of the Earth. So the game is point a very strong magnetic field at the sun. These axions will come through, and in the present, so we had the Primakov effect here once, turning photons into axions, and then we use the Primakov effect again to turn the axion back into an X-ray. And then we detect that X-ray. Pretty simple experiment. So you have a black box and X-rays just start appearing. You point a little bit off the sun and the X-ray goes away. It's a very definitive, very elegant experiment. Only explanation would be that there's axions. This was first proposed by Pierre Sikivi in the 80s. He also did a lot of the work around helioscopes. So taking the phenomenology and figuring out a way that you can test it experimentally. The probability, we'll get more into this in a second, depends, so the probability of converting an axion to a photon depends strongly on the strength of the magnetic field and the length of the magnetic field. You need big magnets. You can also, there's a coherence issue here with the length of the magnetic field, so Carl van Bibber realized that if you introduced helium into the bore of the magnet, that you could get some additional mass range when you do your searches. We'll talk about that in a second. So what does this look like in practice? So this is the CERN Axion Solar Telescope, or CAST. At the heart is an LHC test magnet. So this is a 10 Tesla magnet. And we have to be able to point this at the sun. So inside this very large structure, which is a few meters across, there's two very small bores that are about 4.5 centimeters across. So the idea is that you point this system at the sun during sunrise and sunset. So let me walk you through that. So at sunrise, you actually tilt this thing up so you can follow the sun from sunrise across the horizon up. So the axions stream through this end, get converted back to X-ray photons here, and what you have is, one second, you have a set of focusing optics and detectors on this end. This is the sunrise side. So we have X-ray telescopes to concentrate the signal into a very small region to drive down background. And then we have a gaseous detector and a silicon-based detector. So high quantum efficiency, low background to detect the photons. This system, I'll show you a movie in a second, can track in elevation plus or minus 8 degrees, and it can track in azimuth plus or minus 40 degrees. So that means that we can track the sun for about an hour and a half in the morning and an hour and a half in the evening. So at night, we do the same thing. Now the sun is up here, it's setting, so the photons are going to stream through these detectors. Sorry, the axions will stream through these detectors, be converted back into X-rays here, and we have a different set of gaseous detectors on the sunset side. This whole apparatus is in one of the power substations for LHCb, so we were physically constrained on what we could put in here. So we could only spin it around 80 degrees, and you had walls here which prevented us from putting focusing optics, so just sometimes reality gets in the way of the experiment. This was essentially a recycled experiment, right? We got the LHC magnet for free. It would have just been turned to scrap. And so the goal was figuring out how to safely and accurately point this 40-ton experiment. So let me just, this is a time-lapsed movie. And so hopefully this will play. not sure the computer is unhappy. It's a big file. Let's try this one more time. All right, let me, I'm going to just pop out real quick and see if I can get this just to play. All right, just too much technology for the screens here. Unfortunately, you won't see the movie, but you can download it from YouTube and from the CERN website. That's too bad. All right, let me just pop back into the presentation here. Sorry about that. If anyone's interested, you can come up afterwards and we can show you the movie. In any event, what you have to do during a shift is you have to walk around the structure and make sure that no one has left a wrench. Not that that's happened before on this track. It's not good to have the whole thing jump. It's a very precision machine to be able to track the sun to a few arc seconds, about 10 arc seconds. You also have to make sure that you're not pulling cryogenic supplies out of the cryogenic system. And then also, this is a finicky magnet. It was never designed to work, for 25 years. So these magnets quench. And what that means is you have this very sudden transition from superconducting to non-superconducting state, and you release a tremendous amount of energy. I don't think I've ever been as scared in my life as when that happened, because it's unpredictable, it's a big boom, and then a huge amount of helium is released so that the gas system doesn't blow up, which is good, but it really scares the crap out of you. So this is why we're limited to the plus or minus 8 degrees in elevation. Oh, okay. So it just needed to be loaded in buffer. So yeah, this is definitely sped up, but it's pretty impressive to watch. So there's basically a slow control mode, which happens when you're pointing. And then once you're done with the shift, once you've finished the observational data, then you can drive the system faster to get back to the position for sunset or sunrise observations. During winter, this is a very compressed timeline, so you wind up spending a lot of time and drinking a lot of coffee to keep up to support the morning and evening shifts. And this has been working since 2003. And knock wood, no major incidents other than a couple of destroyed wrenches. So
there's no window?
There's window for, yeah, because the Axion just streams through. We did knock a window right there so that we can make sure that we're actually pointed at the sun. So about a year in, someone said it would be really tragic to spend all this time and money and you were off. So we knocked a hole in the building and then had to negotiate with a farmer to be able to cut down a couple of trees, which was very painful, but that's done. And so twice a year, we're able to verify that the sun, we put an optical telescope on the side of the magnet and verify that we're actually following the sun the way that we think we are. Great question. Okay, so this is the current exclusion space. So Axion coupling constant here and Axion mass. And now I've removed all the astrophysical observations. So this is experiments that we've done. So again, ADMX for the helioscopes, and then everything we've done within CAST here. So this little jump, so CAST has a very large mass region. We lose coherence right around 10 MeV, and we would go up. By putting helium in the bore, we're able to go a little further into QCD models here. So this just has to do with maintaining coherence with the buffer gas. But CAST is still running. It's doing more exotic physics now, but we've really kind of run out of gas. There's not a lot more we can do with CAST to be able to push down and explore these really interesting parts of QCD space as well as test these ALPS models. So if we want to do something different, we need a new experiment. We can't use recycled magnets. We need to build dedicated instruments. And so since we use the Primakov effect twice, it's coupling constant to the 4th power times all these terms. So the most important oomph you can get if you're going to build a new experiment is building a very long and strong magnet. You also want one with a really large cross-sectional area. So instead of 4 centimeters across, like the LHC dipoles, you want 1 meter across. You also need focusing optics to squeeze that putative X-ray signal down to a very small detector, because the detector itself, you need high quantum efficiency, you also need low background. So we need detectors that have about a count a second a year, and that's a lot easier to do instead of having a square meter of detector if I can have a square centimeter of detector. So that's why you need optics. So compared to CAST, the designs that we've come up with, we're about 1,000 times better on the magnet, 50% better on the optics, and more than an order of magnitude better on the detectors. So that's an improvement of at least 20,000, which is pretty awesome, but it's to the 4th power. So it only means we're going to be able to push down in sensitivity, maybe a factor of 10, maybe a factor of 50. And this is what it looks like. It's a beast. It's not dissimilar from a giant radio telescope in terms of the mass and the pointing accuracy you need. So if we can build a 100-meter radio telescope in Green Bank, West Virginia, we can build this system in terms of the elevation and azimuth drive. The idea is to have a 20-meter long magnetic length and to have 8 bores instead of 2. Each bore needs to be about 60 centimeters in diameter. You need to have focusing optics and detectors, and then you need to make sure that that you've got a very clever engineered solution so that you can spin around and observe the sun for about 12 hours a day and do background for the other 12 hours a day. And for scale, here's our 2-meter tall, skinny Swiss guy. So it's a big system. We'll get to that right now.
You don't really need daylight for that to work, right? You can point into the...
You could point in any direction. The reason that we've kind of kept it this way, only pointing in one direction, is just that prevents us from having to build twice as many detectors, and you wind up with a really long tail. You do need accurate background measurements too, so this is just more cost effective to engineer it this way. So LHC, the magnets run at about 10 Tesla, the LHC dipoles. What we've decided here is to go more with a detector magnet like the toroidal Atlas InCat magnets. So lower fields don't have to worry about quench. You can just, once you turn this thing on, you can run it for a decade and it just is going to run reliably. So the field strength in between the coils is 3 or 4 Tesla. So a little detuned, but again, we're buying reliability. We don't have to do R&D in exotic superconductor materials. That's what the CERN experts, as well as some experts from Saclay, advised us on. So just a little bit of detail here. The references are here if you wanted to go through these numbers, but the peak magnetic field is 5 Tesla. The average in the bore for this particular design was 2.5. I overestimated that a little bit. The total mass of this system is right around 250 tons. So you need a lot of mass to control this potential energy that you're building up by having such a large magnet. And so you can see some of the keystone plates and the boxes here to handle both the gravitational and magnetic loads that this magnet's going to generate. The next thing you need are focusing optics. And again, the reason for this is you have a 60 centimeter bore. I would need a 60 centimeter diameter detector. That's going to have a lot of background. So I just want to squeeze those photons into a smaller region as possible. So focusing optic with a focal length of maybe about 5 or 6 meters. It's important to note that, so we're borrowing technology from the X-ray astronomy community, but we don't need exquisite optics. We're making axions in the central 10th innermost core of the sun, so it's about 3 arc minutes across. So if I had a perfectly focusing optic, I'd still see a 3 arc-minute blob of axions. So I don't need to spend a lot of money making exquisite telescopes. I basically need concentrators. And so I'll talk about the baseline technology we're using here from a satellite mission called NuStar. So the idea behind this is that you take flat panel glass, the stuff that's in your laptop or your phone, you thermally form that into a cylinder, and you put a multi-layer coating on that that's tuned to have high reflectivity in the 1 to 10 keV band. So this is all very proven technology. This is what a telescope looks like here. You can make them so that they're 50 or 60 centimeters in diameter. Even though it's made from glass and held together with carbon and epoxy, it can survive launch into space and vacuum in space, so it's going to survive these ground-based applications. There's a few nice things about this approach. It's relatively inexpensive. These telescopes would cost of order about $100,000 each, because it's just glass and epoxy and carbon. And the team that developed these optics, Livermore, Columbia University, and the Danish Technical University Space in Copenhagen are all members of the IAXO team. And we're even able to reuse some of the systems. It's basically a precision lathe that you use to put the optics together. And I'll show you in a second, we've already built and employed one of these telescopes for CAST. In terms of the detectors, it's kind of the same sort of development. This is not that hard to think about an X-ray detector that's going to have high quantum efficiency in the 1 to 10 keV band. The trick is driving down the background. So these gaseous detectors work pretty well. What's crucial for this is having the appropriate shielding. So not just lead shielding, but also things like a nitrogen purge to remove any radon that collects in order to be able to achieve these very low background levels. And so the team from Zaragoza and from CEA have been spending the better part of a decade improving the noise performance, the background performance of these detectors. So some of the key features they've realized is not just the shielding, and I talked about both lead and these gas handling systems, but using radio pure components. So we're actually able to borrow a lot of techniques developed by our colleagues that are doing WIMP searches and picking the right materials to make the detectors out of. And then using offline discrimination to do cuts to throw out background events that might be masking themselves as signal. So the background level we need is 10 to the minus 7 to 10 to the minus 8 counts second per keV per square centimeter. And we've almost demonstrated that level. So this is, it's a little hard to read, but this is time starting in 2002 up to 2015. So there's been a 2-order magnitude improvement, lowering the background level. And we achieved that background level that we need for IAXO with a year-long experiment at Confranc. The challenge there is you have the overburden of Earth in that underground laboratory. How do you maintain that detector performance when you bring it back up to the surface of the Earth? So we're not quite there yet, but there's a robust, well-defined roadmap the detector team is taking. Another interesting thing with this design of having 8 bores is if there's another detector technology, maybe it's some of the CCDs that Fermilab has used for their dark matter experiments, you could swap those in. So if there's another technology that comes along, the same way if there's a different way of making an X-ray telescope, you can drop these in. And that also gives you some independent checks in case you do detect a signal. We've employed this approach of implementing radio pure components, this improved shielding, to couple with this glass slump telescope for our most sensitive results, which let me first show you the hardware and then I'll show you the results. So we included things like veto shields. So these are plastic scintillators coupled with PMTs to reject high energy cosmic background events. This is this little glass slumped telescope here. It doesn't look like a traditional X-ray telescope. It's not symmetric, but it covers the entire bore of the magnet. So we built just enough telescope to be cost effective. And then we took the telescope to Panther, which is a long X-ray test facility in Garkine, and verified that it was performing as expected. And the Saclay and Zaragoza team did the same thing with the detector data. So the gas detector doesn't have great spectral resolution, but it's sufficient to be able to resolve the K-alpha lines at aluminum around 1.5, argon around 3, and the copper K-alpha at 8 keV. And so when you put this together, we were able to, in 6 months of observing, so 6 months of collecting data, we were able to significantly improve on the CAST results that it took us about 8 years to collect. So this shows the power of, so we use the same magnet, but just with improving the optics and improving the background, we are able to, over a very large mass range, improve our search of this, part of parameter space. And again, in this case, we didn't use helium, so which is why we start to turn up here. If we'd put helium in and repeated those measurements, we would have come over here and started to cut significantly into the QCD band. That would have been really time inefficient for the overall project, so we decided to wait until we build IAXO before we do that. And so we have an iron 55 source on one side of the magnet. That lets us prove that this optic is focusing. It helps us understand which part of the detector to look for events from. And so this is where, for a source at infinity, the photons would appear. And so we saw 3 events. We expected 1. That's not a detection, but we use that to set this upper limit. So this both gave us new science, and it also let us prove out these enabling technologies for IAXO. IAXO is going to cost $100 million. Pick your favorite currency, francs, euros, dollars. It's an expensive, large experiment. The funding agencies have been a little gun shy, and so what we did is we said, well, why don't we do kind of a tweener? Let's do a experiment that's going to beat CAST significantly, prove that IAXO works, see if the community is interested, and this has actually gotten very good traction in Europe. So Igor just got a European Research Council grant. We just had a meeting earlier this month with Daisy in Hamburg, the management there. They are doing a light shining through wall experiment, and they're interested in having a broad Axion portfolio. So it looks like what we're calling baby IAXO will be built and sited at Daisy. And the concept here is to prove out a lot of the key elements of the IAXO magnet in this smaller subscale experiment. So the idea is, instead of making it 20 meters long, we're going to make it 10 meters long. It's a lot less mass. We'll still use focusing optics. We'll still use these low background, high efficiency detectors. So it's a way of testing all the key systems, getting Daisy comfortable with doing these particle physics experiments, and then setting the stage for us to build the full IAXO. In terms of parameter space, so this is the potential prospects for baby IAXO. And again, we would not propose putting helium in the bore, so we're going to lose coherence and turn up here, but you see that we improve significantly over CAST. We're also able to start to look at interesting parts of this ALP space, both for the ultra-high energy gamma rays and as well as the anomalous stellar cooling. And if we're able to do the full IAXO, we fully search and either find or exclude these ALPS models here. If we wanted to be a little risk-taking, we could run the magnet at higher fields. If we did that, you'd get another few factors in improvement in sensitivity down to what we're calling IAXO plus. So the approach might be to run IAXO for a year or two. If it's working well, we don't have any issues with maybe the magnet quenching, then we could increase the current, increase the field. This is still kind of to be worked out. So where does IAXO fit in with the broader Axion landscape? There's definitely been a renaissance in the number of experiments that are being fielded, and I apologize, this came out a little dim. So we've already talked about where IAXO can go. What about the other experiments? So what's quite interesting is with ADMX, with MADMAX, and a few other helioscope experiments, we're going to see a broad systematic search of the lowest part of the relevant QCD Axion space, and I apologize, that should be micro EV here. There's some very innovative work going on in the amplifiers and in the cavities that you would need to be able to push the microwave cavity experiments up into higher mass regions. There are plans for this. So I'd say that we should expect a systematic search of 1 to 10 micro EV in the next 3 or 4 years, and the next 4 to 10 years, a search from about 10 up to 200. With IAXO, we're going to go down. So we're coming from the other part of the mass range. So there's going to be this little narrow window here of unexplored space, but I'd say the landscape looks pretty good. So in the next decade, if all these projects get funded and built and operate as we'd expect, we'd be able to search, I'd say, the most interesting part of outer space and be able to search and either find the QCD Axion or exclude most of it. So that's kind of where the broader game is at in terms of Axion searches. There's other experiments on here that we didn't talk about. Ariadne is another one at University of Nevada, Reno, where they're looking for Axion nucleon coupling. Those are much more speculative right now. If those come to full maturity, they might also contribute to this. But this is really the Axion photon coupling parameter space, the ubiquitous coupling in all Axion models. So just, I think, 2 more slides here. So just where are we at with the IAXO Baby IAXO project? So we started this over beers, many beers in fact, at CERN late at night in 2011. First papers on the physics potential and the experimental concepts came out a few years later. DAISY has suddenly become very interested about a year ago. 17 institutions from 10 different countries have joined the project formally. We've defined a management structure, and the near-term goal that the entire collaboration decided on was focusing on getting Baby IAXO designed, funded, and built. And again, it's kind of a twofer. We're going to do some interesting physics, but also wring out all of the technologies we need to build the full IAXO experiment. And we think that we could actually be taking science data in about 3 years if everything aligns well. And then finally, I wanted to emphasize that new collaborators are absolutely welcomed. We are always looking for people to join, and that could be from a phenomenology perspective, it could be from an operations perspective, it could be from the Axion physics itself, or some of this astrophysics or broader cosmology. So please contact us if you just want to learn more about what's going on. And then just to conclude, I mentioned that I was going to bookmark this about Livermore. Jaime and Julia both benefited from the postdoc program at Livermore. So we're very interested in having postdocs come to the lab from wherever they are. We want the best and brightest. Doesn't matter what country you're from. I've got a lot of questions about that today. We have lots of foreign nationals. Julia is a German citizen. Jaime is a Spanish citizen. We just want good scientists to come and contribute to the science that we do at Livermore. So we want them to maintain their university collaborations. There's dedicated funding for people to go to conferences and pursue professional training activities. This is very important. We allow and encourage our PIs or our postdocs to be PIs on grants. We want them to have that experience as early in their careers as possible. We emphasize publishing, and there's not everyone at the lab is a great mentor, but there are a lot of good mentors, and so we pair up the postdocs with people from all stages of their career to make sure that they have a good experience there. So we hope that everyone who comes as a postdoc stays at the lab, but if you have a good experience and you go out and work in the broader community, that's also a success, not just for us, but the broader DOE system. So with that, I'd like to thank everyone for your attention and be happy to field any questions you may have. Please.
So if we go back a couple slides to the final search plot. So I guess the light through walls, that's the gray area at the top. Is there any?
That's Alps.
Oh, okay. So it's not just the
Yeah,
It's also becoming relevant.
it's becoming relevant. I think that the challenge there is that they want to take a bunch of, I think it's Hera 3 magnets, like, dozens of them, and straighten them out and then line them up. It's possible to do that. It'd also be, maybe you just need a really big NIF-like laser, and then you can use those magnets. So we do have a really big laser. So there's definitely the chance that ALPS could push down, or a light shining through wall experiment could push down further. And again, they're complementary because completely different ways of creating the axion would be worth pursuing potentially.
It's always nice being able to have a control.
Yeah, absolutely.
So for gamma rays that are being sort of coming here from this distance, like nuclei, so what is the mass where you would see the time of flight difference?
Ooh, that's a great question, and I don't know that off the top of my head. I understand the question, but yeah, I don't have a good sense of the answer to that.
So in astrophysics, the objects like the pulsars and neutron stars have like probably the strongest magnetic field. Right? So then there's also light from those objects. I would expect some of the constraints from those objects. I'm not sure when you show some of the astrophysical constraints, people take those into account.
Yeah, so the challenge we have with if it's an astrophysical riddle, like how come that star is cooling faster than expected, that's easier to do than saying, let's say from a neutron star, let me look for some modulation in the X-ray signal. And the reason for that is L squared, right? Or D squared, it's the distance. And so it's super intense fields, maybe very strong, but that D squared is a killer. And so you're spreading that luminosity out over kiloparsecs. And so that's why we went after it. It's not that the sun is the best emitter of axions, but it's absolutely the closest by far. So we've done some calculations, and it's orders of magnitude off if you went after a bright, relatively nearby neutron star at a kiloparsec. Yeah, so this is a great question. The challenge there is, in fact, Julie and Jaime will hopefully have a paper out on arXiv soon looking at new star data. So the idea there is that if you could point the X-ray telescope at the sun and you had axions being converted in the solar corona magnetic field, you'd actually suddenly see a bright emission spot in the center of the sun. That's as we would say in Boston, a wicked hard problem to do because that magnetic field is dynamic, it's twisted, and so you can kind of get an upper limit, and that's not on QCD, that's on ALPS. It would be in this part of parameter space here. So it is a test of ALPS, but not of the QCD axion.
Could you comment on the light shining wall experiment in Europe? Are they going to build it or not?
Yeah, no, this is Axel Linder's project, and it's, as far as I know, ALPS 1 is underway, and it's kind of gone through a few different nomenclature changes, but ALPS 2 is definitely on the books, not yet built, but ALPS 1 is built and taking data. Please.
I have a very basic question. So the term that we've written at the beginning for the Axion term,
Yes.
contain gauge delta, right?
Yeah.
So these are the gauge fields.
Correct.
Yeah. So since you're looking at the CP violation in the chromodynamics, I would assume those are gluon fields, right?
Those are,
Gluon?
yes.
So why would these axions couple to photons?
So you're now,
I understand that
yeah,
these were the Maxwell, whatever, F at tilde.
right.
But that's not what you're using. So what connected?
So I prefaced this earlier by please don't ask me to do any field theory calculations because I'm a simple knuckle-dragging experimentalist. So I'm going to have to ask someone in the audience if you've got a simple explanation for why that is. I mean, it's just, that's all axion models as far as I know. I think we can go back. Maybe I've got one other part of the theory explained.
So quartz can grow
let me see if this pops up here. I think this Feynman diagram, hopefully. Let me see if I can. There is this wonderful lag. All right, well, hopefully this Feynman diagram will pop up, and in the meantime, maybe if there's any other questions while we wait for my laptop to catch up.
Is there a direct scattering diagram for a couple of axions? Like, are they self-interacting?
That, I mean, sure, at some at some absurdly low level, but to
But at sort of big level.
yeah, no, it's basically once they get converted, once you take that photon, convert it to an axion, they stream out and they're not self-interacting at all for this detection mechanism. And I apologize. Let me see if. All right, well, I think I've taxed my. Maybe it will pop up. Any other questions? All right.
I basically got that.
Perfect. That's what I was hoping for, was a little assist from the audience. Any other questions? Great. Well, thank you again.